right, we are back to lectures here on signal processing. What we want to talk about is the representation of signals. In particular, we're going to start thinking a lot about Fourier representation of signals, and we're going to talk about Fourier series. This is one of the most important transforms that we will ever explore in the sciences, is the Fourier transform. And what it is to take a signal and represent this as cosines and sines, which are a basis set of functions that are going to allow us to do quite a bit from a signal processing point of view. And so what I want to highlight is why we want to use these and the relationship to LTI systems and how they actually are pretty transformative tools in building up signals and processing signals. Okay, so Fourier series is going to be a way of thinking about representation of a signal. Another way to think about it is the Fourier series are going to be a coordinate system we're going to use to represent signals. So one way to think about it is you're going to have things like cosine t, cosine 2t, cosine 3t. These are essentially harmonics of a basic signal, and we're going to build up a representation of any signal in terms of these harmonics of cosines and sines. And we're going to find that it's going to be a really powerful representation. And more than that, we're going to find that these, in fact, are eigenfunctions of LTI systems, which is really what makes them so powerful from just a purely mathematical manipulation point of view. Okay, so this goes back to the ideas of Joseph Fourier. Here he is. He was... this was a time period in which he was alive. He actually went on an expedition with Napoleon through the deserts of Africa and was trying to figure out also how to keep the temperature of this wine collection of Napoleon at the right temperature. How far do you bury it in the sand to keep it at a perfect French wine temperature? And this is also where he started then trying to study the heat equation and understanding how to represent that, for which Fourier modes are in fact the natural basis to do this. Now, this idea of representing any signal with sines and cosines was pretty revolutionary in many ways, and Lagrange worked very hard to say that in fact this was a terrible idea. He did not believe that the way that Fourier had proposed to do this was the correct way, that these were great functions to represent any signal. And in particular, he thought a lot about if you have signals that in fact are have cusps or other things like this, there's no way a very nice smooth sine and cosine function could represent it. But in fact, you can represent it, and in later theorems we showed that you can represent any function as a sum of sines and cosines under mild conditions, and we will talk about those as we go forward. So there's Fourier, and really a remarkable contribution to science in developing what we call now the Fourier transform, or the Fourier representation of signals. And so here's the basic idea. So when we think about a signal in time, x of t, what we're going to do is say I can represent that signal as a sum of cosines and sines, where when I do this calculation, my main job is to calculate what these a of k's, what these b of k's are, right? So that's kind of what I'm after, is trying to get these coefficients, because I know what I want to use, which is cosines and sines here. So I'm going to use those as my basic basis set, and I just need to figure out how to get the right values of those coefficients, a of k and b of k, for any signal x of k. Alternatively, we know that cosines and sines can be written as complex exponentials. So instead of using cosines and sines, we could use here e to the I omega kt. We know that this is in fact sines and cosines, right? So this here are sines and cosines. We could represent signals in that, and then we'd have to, again, just figure out how to calculate the coefficient c of k. In either way, what we're trying to do here is to take a signal and represent it in a new coordinate system. And I want to emphasize this idea that this is in fact a coordinate system of infinite dimensions, where these are essentially the basis vectors in this new coordinate system. Or if I do exponential, it's these. So that's the fundamental idea behind doing this Fourier representation and behind a Fourier transform. So let's talk about why we want to use Fourier, because it turns out that it has some very nice properties. In fact, if we think about going back to LTI systems, linear time invariant systems, this is what we've been covering for most of the course is building up some of the ideas of linear time invariant systems, then one of the things you're going to find is for an LTI system that in fact, if you put in a signal that's an exponential to a continuous time system, what you get out is that exponential again times some coefficient. This is going to be some integral, but it's going to be a number. Same thing with the discrete system, LTI. You put in z of n, and if you use this representation, what you get out is in fact back to the z of n times some number h of z. Another way to think about this is basically telling you that this E of st is an eigenfunction to the LTI system, and we'll dive down on that just right now, just so to make this very concrete. And oftentimes in most systems, if you know what the eigenvalues and eigenfunctions are, you know almost everything you need to know about that system. And so this is setting up a framework for us. It's essentially saying that using this Fourier basis in an LTI system is, in some sense, the absolutely correct coordinate system you want to be using in that system. Okay, so that's the main point here. Exponentials are eigenfunctions of LTI. Okay, so let's go back to an LTI system, because this is what we were considering in LTI. We were saying, okay, an LTI system, right, is you take an initial signal x, you convolve it with the response h, and you get the output y of t, right? So this is how we were formulating what we would get out of an LTI system under some signal comes in, it hits the system, it produces a response h, and our signal out is the y of t, okay? So one way to think about this now then is we're going to take into the system, we're going to not just consider any signal x, but we're going to make this signal, in fact, an exponential. So there's an exponential, so not just x of t, but now e to the s, t minus tau. So this is our exponential signal, and the question is, what happens if I put an exponential signal into this? And what is the mathematical consequence of this? Well, let's go ahead and focus on this equation here. So I'm going to bring it back out. Here it is. And notice I'm going to do this integral, but e to the s of t minus tau, I can always break this up into e to the st times e to the minus s tau. So the e of st can come out of this integral. Remember, I'm integrating with respect to tau, and the e of st is independent of that. And so I can pull this directly out of that integral, this convolution, and what I end up with is just an integral with just tau left over here, where I'm integrating from minus infinity to infinity. Of course, you can see there's an s right there, so there is some dependence upon the parameter s, but for the most part, one can just think about this as this is going to be some number that depends upon s times e to the st. So I came in with a signal that was an exponential, I came back out with that same exponential times a constant. And so this is what's so powerful about this representation in Fourier for LTI, is because when you're an LTI system, these are the eigenfunctions. So all they do is the exponential comes in, and the constant h of s tells you whether, essentially, depending if h of s is bigger, that it amplifies that exponential. If h of s is less than 1, it decreases that exponential signal on the output. So this is a really powerful concept, and what we're going to do is use this as the basis of a lot of signal processing, just to simply understand, if I run a signal through an LTI system, what happens to these coefficients for every single exponential, or in our case, when we have cosines and sines, what happens to each frequency as I run through this LTI system. So a more abstract way to think about this is I'm going to introduce this notation of an operator L. So there's some operation on the signal, x, that produces y. Okay, so operator L essentially is what we just showed there. It's like the action of the system when I hit it with a signal. What is the result? L essentially captures all the physics of the system, all the things that happen when a signal comes in and acts in the physics with whatever system you're looking at, and then it's going to produce a output y of t. Okay, so y of t is this operator now acting on e of st. Okay, and what comes out is that operator L I just showed you. It comes out with some constant back with est. Okay, so another way to think about it is the operator comes in with acting on e of st, comes out with a constant times e of st. So the e of st, in other words, part of the reason I did this is because now you can clearly see this is the eigenvalue problem right there of this operator. So the operator comes in. This is an eigenfunction because you get back exactly that same function times a stretching factor. So it either got bigger or smaller depending upon the value of h of s. And this is the eigenvalue. Okay, so h of s is the eigenvalue to the LTI system for a given signal, and e to the st is the eigenfunction. Okay, so that's really nice because now what we have is we have a way to very clearly identify what happens for every single exponential that comes in. And so what we're going to do is represent our signals as a sum of exponentials, and all we have to calculate is what is the action on each exponential and add the solutions together. Remember, it's LTI, so it's linear, which means superposition holds, and we can just add the signals back up and use this property here of the eigenfunctions. Okay, so that's the big idea, and it's a really powerful one. And let's look at it now in the context of a discrete system. So in a discrete system, we have x of n, okay? Z of n here is, so this is how it's defined. It's an exponential in the discrete case. Same idea, which is I have an output response, y of n, and basically I'm kicking the input here. So I bring in a signal x, I hit it, and h is the response of the system. So remember, we convolve the input signal with the convolved response h, and that produces the output y. Okay, so that's this representation of an input-output of the system, and what we're going to do now is plug into our signal here. We're going to put in not just any x or any signal, we're going to actually put in this exponential. So when we do that, this is now h of k, z of n minus k. But notice here, z of n minus k is z of n times z of minus nk. Now this is a sum over the k, and so z of n itself can come out of this sum. So here it is. I can pull the z of n out, and what I'm left with is h of k, z to the minus k. And then this is just a summation, just like before. If I sum over all of k, this is just some number. It's whatever it is. So depending upon what the h is, the response function, summed up over this set of exponentials here in the discrete time case, I get some number that I can compute, and then this is the idea. So y of n comes in, I bring in z of n, I get back z of n times a constant, and it's exactly like what we had in the continuous case, which is h of n is just some number times z of n. So I bring in z of n, I get back z of n with a scaling factor h of z, which either makes that specific z of n bigger or smaller, depending if h of z is bigger than 1 or smaller than 1. So this is a really nice idea. So it just sets up the eigenvalue problem also for the discrete case. More broadly, here it is. Again, now in this notation, there's some operation that acts on z of n, okay, and this is the action of the physics of that system. What comes out is the zn of, again, times this h of s, and so here you go. Those are the eigenfunctions and eigenvalues. So once again, you have these sitting right there for yourself as these important pieces of information for you, which means now I'm going to do a linear superposition, and if I know that each single one of these signals is actually an eigenfunction to the system, then all I have to do is compute the eigenvalue, and then I can tell you exactly the response of the system because I've got the right coordinate system, which are these exponentials, which are the eigenfunctions to this LTI system. So that's the main idea. And then this allows us then to consider multiple signals. So if we want to look here at multiple signals, we can take something like this here. This is a signal which is represented as a sum of 3 exponentials, right? S1, S2, S3 are the 3 exponential coefficients. And so you can ask the question, what happens if I take this signal into the system? What comes out? Well, what comes out is I have linear superposition. So for each individual signal, for instance, the A1e to the S1t, it comes back out as A1 some constant. This is the eigenvalue that comes out of the system times e to the S1t. Same thing with e to the S2t comes out with, again, the eigenvalue of that specific exponential, and e to the S3, you get it back with just the eigenvalue. So these h's represent either a scaling factor, either it stretches or compresses the signal, makes it bigger or smaller, depending upon what the value of h of s actually is. So this is the this is the response to each individual exponential, but since it's linear, I can add the responses together, and this is what it produces for us right here, okay? So what I have here is a representation of this output signal is the response to signal 1 exponential, response to signal 2 exponential, response to signal 3 exponential. Okay, so that's the linear superposition playing out directly here for us in this system. Okay, so more generally, if I had a signal that was made up of a sum of exponentials, then the output is the sum of exponentials, again, multiplied by this eigenvalue for each of the exponentials. Okay, so there's that input-output relationship. So this is really nice. So the fact that these are eigenfunctions to the LTI allow us a very simple construction of the input-output relationships. And so this is why we want to use exponentials in LTI systems, or Fourier representations, which again are just our exponentials. Okay. Same thing for the discrete case. Again, I have a signal x of n, a of k, z of nk, and if I run this through the system, the output is exactly the signal back with each of the coefficients being stretched or compressed by h. So you can see our job then is twofold. Our job is first, I have to determine if I want to do this expression, I have to take any signal and represent it as this sum, which means I've got to determine the a of k, and that's the first job. Second job is once I have that, I have to determine the eigenvalues, this h. And once I get those two pieces of information, I'm good to go. You can now construct any input-output relationship that you want. So that's what we're going to focus our attention to now, is starting to think about what do we have to do to compute those coefficients, and how do we compute those eigenvalues. So I want to generically take any signal, represent it as a sum of Fourier modes, and in fact that's exactly really what Fourier was advocating. And then you can see once we can represent a signal generically as a sum of Fourier modes, then all we have to do at that point is figure out how much of each Fourier mode do we have and what are the eigenvalues as it goes through our LTI system. So let's come back to this idea of Fourier and periodicity. There's an underlying assumption with Fourier that in fact I have a periodic signal. So we're always going to be working on some kind of, let's say, domain of size t here, right? That is periodic, okay? So that's an important factor in our mathematical consideration, is we need a basic underlying period for the system in which to construct our solutions. So there's a couple ways to think about representation with period t. One is you could do something like this. I have a cosine of omega naught t, or I have a e to the I omega naught t. And for us to have that period of capital T, then we have this fundamental period t is 2 pi over omega naught. So we can definitely construct these where we have this relationship where we say, well, the underlying period of each of these signals is 2 pi over omega naught. So that's how we would construct, let's say, the underlying fundamental period. And from that fundamental period, now we're going to start expanding in harmonics. So here's going to be our basis functions. We're going to basically take some function, 5k, which is going to be our exponential. But notice what I've done here. Before, I had just e to the I omega naught t. Now I have e to the I k omega naught t, where k is an integer. So k can be 0, plus or minus 1, plus or minus 2, and so forth. And so now all these are, in fact, all these harmonics have the same period of capital T. And so now I have an entire set of functions that are, in fact, have the same period. And I'm going to use these as my exponentials for representing any generic signal that I want. Okay? So there's going to be the harmonics I use to represent a signal. So a Fourier series representation then is to say, take a signal x of t, represent it as a sum, negative infinity, infinity, of a of k e to the I k omega naught t. So all of these exponentials, because I've picked this omega naught as the fundamental base frequency, k here, average type, k equals 1, 2, 3, 4, negative 1, negative 2, negative 3, they're integers. They all have period t. So on some domain of period t, these are all my periodic functions that if I add them together, I'm going to be able to construct any generic solution. The other thing I want to say about these functions is we're going to start seeing this later, is that they are actually orthogonal to each other. So each one of these functions, e to the I k omega naught t, is orthogonal to e I p omega naught t, where k and p are different. So each different k value, when we take an inner product, is 0. It means they're orthogonal. And this is actually the key to sort of this representation, is that essentially using these base functions, so for instance, cosine t, cosine 2t, cosine 3t are all orthogonal directions. So when I represent a signal, it is like a coordinate system where everybody is in an orthogonal direction to each other, just like we would use in using an XYZ coordinate system, except now I'm going to an infinite dimensional space, but the same thing holds there. These are orthogonal functions, and so this is essentially one way to think about it, is this really amazing coordinate system that's infinite dimensional, where I'm just using, again, an orthogonal basis. Okay? So let's take an example of what some of these things might look like. So here's a signal, and I'm going to represent k equals negative 3 to 3, and here's my signal in terms of exponentials. And we can, for instance, just plot this signal where we make some assumptions about what a naught, a plus or minus 1, a plus or minus 2, or a plus or minus 3 are. We just give it some generic values here. And then we can just say, well, what does that signal look like? Well, if you expand that out, this is what it looks like. 1/4 of these two exponentials at ik 2 pi l, and then 4 pi and 6 pi. So this is when k equals 1, 2, 3, or plus or minus 1, plus or minus 2, plus or minus 3, and 0. And notice here, when we did this expansion, because I assumed the coefficients were the same for the plus or the minus, this actually collapses down. I can combine them into a real expression, which is this here. Okay, so that sum of signals results in here, this kind of expression, which then if I start to plot it, here's what the first mode looks like, x naught. So if I just have the sum start from 0, this is it. Now I add plus or minus 1. Here's what it looks like. Here's the x1 component that's there. It's just a cosine with a certain period, 2 pi. And I'm going to add these. So it's going to be this x naught plus x1. So you notice x naught is just a constant. x1 is an oscillation. You add them together. Now it's an oscillation offset with a constant. And then here's x2 cosine 4 pi t. So it's twice the frequency of this here. Now I add them together. I get this. And then I add the third component, k equals 3. This is a more highly oscillating piece, and then you add them all together, and it's this signal here. So you can see, you can start constructing pretty amazing signals. And what Fourier said is I can represent any signal, even discontinuous signals, in terms of these cosine and sine bases. And you can start to see, as you start adding these signals together, you can get very rich representations. But as you'll see, if you go to infinity, you can have functions here that don't look sinusoidal at all. They don't look periodic at all, but you can still represent them with these basic periodic functions. And this is something that Lagrange always pushed back on Fourier for, but Fourier was right. And in fact, Lagrange held up publication of this work for decades, but he was just wrong. And they had no computers to visualize this, but we do today, and you'll see an example in the next lecture of how well this works in representing any signal. Okay, so what if we want real signals? So right now we have this complex representation, right, with e to the I k omega naught t. But really at the end of the day, this is just a handy notation. It's easy to work with this, but my x of k is a real signal and I want a real output. So, if you want that to happen, then what you want is x of t and its complex conjugate to be equal. So in other words, you take x of t, you take its complex conjugate. In other words, where I is minus I, you want them to be the same. So you have this relationship here then. Here's x of t, here's x star of t, okay? And you want those to be equal, and the implication is then that the if you take the complex conjugate of the coefficient of k, it has to be equal to a of minus k. And by the way, this relationship is exactly what we used in the previous example, because if you have this thing holding, these things will add up to produce real signals. Because what you'll get is sines and cosines directly, because the negative part will contribute with the positive. So if k equals -3, we'll contribute with k equals 3 because of this relationship to produce, let's say, a sine or a cosine. So that's a nice feature, and you can always then guarantee signals are real if you have this property here. Okay? So the last piece we have to do is determine, how do we determine then these coefficients a of k? I give you some signal, x of t, you can plot it, and I say, well, I want to represent that signal in terms of these Fourier modes, right? So I have these Fourier modes here. The only thing I don't know then is how to get this a of k. And this is what we're going to do now. We're going to use this idea of orthogonality. In other words, I've already said that essentially these are forming an orthogonal basis. So the way you're going to get this a of k is we're going to basically take inner products. That's our whole game here, is take inner products. What do I mean by inner products? I'm going to multiply both sides by e to the minus n omega naught t. So if I multiply the left, this is what I get. I multiply the right, this is what you get. And then I'm going to integrate both sides of these equations over a period from 0 to t. So it turns out, over that period, that's when these signals, in fact, have their orthogonality properties. So this is always 0 unless k is equal to n. So that's what I mean by orthogonality. So this is this orthogonality condition here. This integral over 0 to t is either t if k equals to n, or it's 0 for anything else. Okay? So notice what happens then. This sum is 0 everywhere except for when k is equal to n, and then finally there's a contribution of t. So ultimately what that leads you is to the ability to compute a of n, which is the following. A of n then is 1 over t, 0 to t, the signal x of t times integral of e to the negative I n omega naught t. So you do this integral, divide by t, you have the a of n. So you have the coefficient for the nth frequency in your hierarchy of Fourier modes. Ultimately, here's our main result for this Fourier series representation. What it tells us is I can take any signal, here x of t, and I can represent as a Fourier series a of k e to the I k omega naught t. So here's the exponential representation. I know that these are eigenfunctions to an LTI system. I just have to determine the a of k when I make this transformation to this new coordinate system. But here is the a of k, just here. We got this through basically doing orthogonality conditions on those functions. So all those a of I k omega naught t are orthogonal to each other, and you get this relationship here, a of n is equal to this number. So this is just, you integrate this up, you get a number, and that's what goes in right here. So this is how you would construct a Fourier series representation. We're going to do more of this as we go forward, because we're going to spend quite a bit of time working with Fourier series. Remember, at the heart of all this is our LTI systems. And what I've just showed you is exponentials are in fact the eigenfunctions of these LTI systems. So they're the natural representation to be working with. And so all we have to do is figure out how to take any signal, move it into these exponential representation, in particular exponentials with purely imaginary components. We're not so interested in exponentials that have positive real part, positive negative part, because one of them goes to infinity, one goes to 0, but these, the ones with purely imaginary components, oscillate and go on forever. So this is the first lecture, really, of starting into this idea of Fourier analysis, and we're going to spend quite a bit of time here because it is, in fact, the fundamental tool we want to be using for solving these LTI system problems.